Okay, 725. You have seen slope, average rate of change, and instantaneous rate of change now. So let's look at application. So 122. Most days Shane is frequently interrupted after he puts up his mid-morning coffee. All right, by the time he remembers to remove it, it's usually cold, room temperature. Shane is very picky and will drink coffee no less than 160 degrees Fahrenheit. Since the interruptions are never consistent, Shane returns to the coffee cup at different times each day to find it undrinkable. He wonders how long it takes for the coffee to drop below his acceptable temperature and decides to take some readings. So we have a table of readings. Give your estimate for how rapidly the coffee is cooling when T equals 5 minutes. Well, if you look, 5 degrees, 4 degrees, maybe 1 degree. So probably, if we're looking at an estimate there, maybe 1 degree per minute at that point. B, after carefully analyzing the data, Shane concludes that the function, so now we have a function, C of T, equals 70 plus 120 times 0.983 to the T. Approximate the temperature of coffee after it has been removed from the mic. Using the function, calculate the rate of the coffee, the rate at which the coffee is cooling at T equals 5 minutes. Okay, so we're talking about instantaneous, right? So what we have to do here is plug in that 5 and 5 plus H, or we can do like we have been is really, really close. So you could do like 5 and 180, and then you could do like 5.001 and plug in and go. Okay, let's see if I can get a Desmos scientific calculator up here. Let's go scientific, and let's see if we can do 0.983 raised to the 5.001, enter, times 120, enter. Oh, can we get this answer times 120? Let's do 0.91782. We'll just go there. Right, so that's 110 plus 110.1384 plus 70 obviously is 180. So this is 180.13 or 14. Let's say 14. Okay, so now we would go 180.14 minus 180 over 5.001 minus 5. Right, obviously we're going to get 0.14 divided by 0.001, and we get 140 there. Did I do that right? Maybe. Okay, so we get 140. I don't think we did that right. What did I do wrong? Let's go. Answer minus 180.1384, enter. That's better. So this is let's do this. So if I plug in 5, I didn't actually get 180. I got 180.1409. So rounding wise, right? So you end up getting that divided by, answer divided by, That divided by 0.001, and you get 2.55 degrees per minute. It's a little better. Okay. How long will it take for Shane's coffee to cool to 160 degrees? So what we would do there is take this equation and we would solve for 160. Okay. So you got to have a calculator because you got to be able to do a logarithm here. But we're going to subtract 70. Should get 90. Right? And then we're going to divide by 120. Right? Should get 3/4. And then we're going to do a logarithm. Right? So you would do log base 0.983 of 3/4. And see what it gets you. Right? So let's see if we can find log. We need log base. All right, so if we do log of 3 or 0.75 divided by the log of 0.983, enter, we get 16 minutes, 16.78 minutes. Okay, is the temperature of the coffee changing more quickly or more slowly over time? It should obviously change more slowly as it gets closer and closer to room temperature. Okay, 123, a boulder falls off a sheer cliff to the ground times 0 is modeled by the function. So we have height is negative 16t squared plus 124. How long does it take the boulder to hit the ground? That's when, well, if we want this to be 0, height to equal 0, right? And we're solving for that. So negative 124 divide by negative 16. We get t squared equals, so let's do 124 divided by 16, right? We get 31 over 4, and then we'll square root that. And so we'll go answer square root, or it's going to make me do that one first. Square root answer, and we get 2.78 seconds to hit the ground. Okay, what is the average rate of change of the boulder over its entire fall? So we got a 0 time with a height of 124. We got a time of 2.78 and a height of 0. So we'll do 0 minus 124 over 2.78 minus 0. So we're going to get 124 divided by 2.78, and we get a negative 44.6 feet per second. Entire fall. What's the instantaneous rate of change of the boulder at t equals 1.392? I would use my other t as 1.393 seconds. Okay. Just get really close there. And then plug that back into the function, right? So we could do this. So 1.392 squared times negative 16 plus 124. Plus 124. So this is 90, let's just say 93 feet. All right, then we'll do this again. 1.393 squared times negative 16 plus 124. And we get go back here. Times negative 16. There we go. That's better. So 92.95. So 92.95 minus 93 over 1.393 minus 1.392. Okay. 92.95 minus 93 is negative 0.05 over, right? And then you have 1.393 minus 1.392, right? So 0.001. So negative 0.05 divided by negative 0.05 divided by 0.001. And we get negative 50 feet per second. Okay, what is the significance of the result from part C? It's the rate at which it's falling at that time. It's actually faster than your average velocity, right? Like it's faster at some point in time. Okay. All right, 124. We got a man 6 foot tall walking at a rate. All right, so hold on. So we have this diagram. We got a man that's 6 feet tall. We got a light that's 10 feet tall. He's walking away from the light at 4 feet per second. Okay. We have an X distance. We have an S distance, meaning S meaning his shadow. Okay, make a prediction as he walks away from the light. What is going to happen to his shadow? That's just you predicting. Okay, B, how long is the man's shadow when he is 10 feet away from the light? So when X is 10, where are we at, right? Well, this is similar triangles. So we have the big triangle, which is 10 over 10 plus S, or X plus S, and it equals the small shadow, small triangle, 6 over S. And then we can solve this, right? So you got 10S equals 60 plus 6S. Then you have 4S, equals 60 divided by 4. And S is 15. So his shadow is 15 feet long when he's 10 feet away. If he currently casts a shadow 12.5 feet, how far is he from the light? So now we're doing the same thing. We have 10 over X plus 12.5 equals 6 over 12.5. So we have 125 equals 6X plus 0, carry the 3, 18, 19, 20, 21, 1, 2, 6, 7, 8, 10. 81. Okay, so we got 81. And then subtract 81. You'll have 6X equals 44. And divide by 6. Right? And X equals what? 7 1/3, 7.3 repeating feet away from the light. Okay, revise your prediction if you need to, right? Write an equation to calculate the length of the man's shadow in relation to his distance from the light, right? So what we have is 10S equals 6X plus 6S, so 4S equals 6X. And then obviously we could solve for shadow and make this 3 over 2X equals S. right? So ever how far distance is he away, it's 3 over 2 that times the shadow. Calculate the average rate of change of the man's shadow, right? Like it is this. It's linear. Okay, it's linear. How does the fact that the man is walking at a rate apply to this situation, right? It doesn't. It doesn't matter how fast he is walking. Okay? Cool. Learner log.